Swayam Prabha. Digital India. Educated India.
We'll continue a little bit a discussion about our CD-ROM drive. There are a lot of fundamentals that we saw last time with respect to it. We'll just kind of brush up some of the things again and proceed then for some kind of a conclusions that we can draw from this exercise. Okay, so let's go ahead and have a look at some of the. Okay, so now what we saw, I will quickly go through here. Okay, so the goals that we set was to kind of develop some kind of a philosophy for this design of mechatronic systems and appreciate some of the things, that solutions that are already existing in the existing devices. Okay, so let's see what we did. We did lot of things for CD-ROM drive, and you can see if we started off with this CD surface and thought about different kind of ideas that can come up for looking at this data and registering it digitally into the computer. And then we came across these multiple systems. Okay, so CD ejecting system, or the gross positioning system, fine positioning system, something like that. Okay, so this summary of these systems is something up here. Okay, so these are the main systems that we saw: the gross positioning system, then the fine positioning system, and then focusing system, and then CD tray handling system, and CD rotating servo system. Now this CD handling, tray handling systems, servo system are something which we have not, we have just seen the CD tray handling system, but servo system or CD rotating servo is just a motor which will kind of get a drive at a speed which is controlled by the position of the device. So we'll talk about that a little bit maybe, but it's not very it's just maintaining the speed to a certain extent for the CD disk. And maybe I can tell you right now only that these CD systems are constant linear velocity systems, which means the linear velocity at a point on the surface of the CD which is under the CD head, okay, under this laser, that velocity will be constant. Okay, so as we know that okay, if I rotate the CD at constant angular velocity, then the linear velocity at multiple points on the surface of the CD will change its omega r. You all know that. Okay, so to maintain this velocity constant here, we want to let linear velocity to be constant at the surface here. I will need to vary the velocity of angular rotation of the CD in some kind of a way. Okay, and that can be maintained by using something called phase lock loop kind of a drive for this motor. Okay, so this is a BLDC kind of motor, brushless DC motor. Okay, and it is controlled by speed is controlled by using this phase lock loop kind of a drive, and its drive and other systems we'll see a little later. Okay, it is like a three-phase kind of a motor. Three terminals are typically output for BLDC motor, and we control these phases to kind of maintain some speed of a drive. Okay, so that is a disk or servo system for the CD which is rotating, and we'll have a chance to see CD motor sometime. Okay, or maybe I can flash you some picture of it. Okay, so if you see this, maybe if I go here, you can see this is opened up CD servo motor, and its cover you can see it up here. Okay, so this is the cover of the motor, and this is the motor opened. Okay, so you can see that, right? This is a motor and this is like a cover of a motor. This cover will have a magnet inside, and on the top there is some kind of a disc here. Inside that there are balls. Okay, if you just move this around, you'll hear some sound of balls there. Okay, think about why those balls are present up there. And if you see this, notice this motor, on this motor at one point you'll find there are this maybe I can rotate it like that and show you here at this point. There are, if you see there are these small little sensor that you see up here. Okay, where my finger is. Okay, those are Hall effect sensors to sense the field. Okay, there is one Hall effect sensor, another one is up here. Okay, so those are Hall effect sensors. Okay, so that is a mechanism for CD drive. Okay, disk drive basically. Then what we saw, we saw various these subsystems and these components and things like that. So you remember all these different things that we saw, and then this is a mechanism, like some kind of a way to kind of prevent a backlash in the system, and the stepper motor that is used for driving this. And this is another kind of a fundamental. We saw that okay, you need these two supports to guide on one side, and only one single support can be there on the other side is okay. If you start putting both the supports on the other side also, then if the alignment of these two rods is not exactly parallel, then you'll see that the drive will jam in no time actually. Okay, so if you start driving at some position, you'll find that the system gets jammed. Okay, so that is what we don't want to have. Okay, then this is another way of preventing backlash. Okay, by using spring loaded two racks with you give kind of a pre-compression in the spring, so that the two racks are getting pushed away from each other, and then you engage them into the pinion teeth, and then this mechanism will start working. That okay, the one rack is pushing on the pinion tooth on one side, and other rack is pushing on pinion tooth on the other side of that other side of the gap. So that way you'll find this arrangement works for preventing the backlash. So you move now pinion in either direction, you have a contact that is happening with the rack, on one side with the lower rack and on the other side with the upper rack, say for example. Okay, so now in fine positioning we again saw that okay, for fine positioning we need to have a compliant kind of a mechanism which guides the system to go in a finer motion. Now why this kind of a compliant beams are needed, that beams that you see here, why they are needed here? Okay, why don't we provide this guide by same way as we have provided with some kind of a rod or some kind of a support to guide? Okay, the main reason for that is friction. Okay, so friction is the reason which prevents us. If you remember the mobile example, if you push something, the friction is what prevents you to kind of do fine positioning. Now when we have this motion coming up because of the compliance of some linkages, or some linkages are bending and getting that motion in place, then actually what happens is you are preventing the friction to happen. Okay, so there is no friction in this motion that will happen, and since there is no friction, then all the nonlinearities in the mathematical or in the physical sense coming because of the friction, they are gone. For example, when you reverse the direction of the motion, then friction force changes its direction. That is a sudden kind of a discontinuity in the friction force. Okay, which is not desirable. That is a non-linearity. Okay, so that's why like many linear controllers for such a fine application may not work very well if the friction is present. Okay, so friction is handled in this case by changing the design in the mechanical domain such that you don't have the friction coming into the picture. So this is like one of the kind of characteristics that we are talking about, that okay, you change the mechanical domain so as to have ease of control implementation in the electronics kind of a domain or electrical domain. Okay, so because we saw in the presence of friction, it is very difficult to control the system or very fine position the system very accurately and reliably, robustly all the time. So that is the reason. Okay, so this system is serving for two purposes. One is like fine tracking, that is there, and other is like the fine focusing servo. Okay, so this is a focusing. These two servos are happening, and we saw in the last class what are the sensors to kind of have those servos working. Okay, so what is the feedback that they'll get is where we stopped in the last class. Okay. So here, like you can see all these kind of things very clearly. Okay, how the coils are placed. Then there are magnets, and then this is a lens from which the laser beam is coming. And then this is so the magnetic field direction one can see here. So one can kind of like do a lot of kind of thinking here, saying, okay, oh look, how these coils are running, and based on that, like can I know okay which direction when the current is passed, which direction motion is going to happen. If I want to move it in one way or the other way, how this coil should get energized, and all this kind of thinking one can do. It's not a big issue, but we'll see. If I don't think we need to do that in this part, but if needed, one can do all that kind of stuff. Okay, so here when we came for the sensing mechanism. Okay, so first, like the again I'm explaining this for the sake of understanding. We have these three beams that are focused on the surface of a CD. The central beam is for the data, and then these two side beams are for making sure that you are on the track or you are on the proper data track. So how that happens is what we want to kind of see. So there's some kind of a system here, but I'll explain it first with respect to the optics ray diagram, and then we'll come back to these elements, how these elements are now implementing the same ray diagram. We'll talk about that little later after the ray diagram is done. So let's come to this photo diagram. Okay, so this is a photo detector on which these are four elements A, B, C, D here, and E and F are on the side. So let us go to the ray diagram. So you remember that okay, we have this kind of a facility is there where your three beams are going to fall, their reflections are going to fall on these three places. One is here, the center beam will be here, and second side beam will be here. Okay, and E and F are full photodiodes. It is there is a like a little larger area in E and F than in this ABCD case. Okay, so now let's see the ray diagram. Okay, so the optics, what happens actually is the laser gets split into three beams as we have seen, and then it is made to fall on these multiple mirrors or whatever, that reflectors, to get basically to take it on the surface of the CD. Okay, and when it comes on the surface of CD, that's when it looks like the picture that I showed you about the actual CD surface image. Okay, then it gets reflected from the surface, and then it travels back. Okay, now because there is a beam splitter here, the beam splitter will have a function that okay, so look, even while going this beam would have split and part of the beam would have gone here, but we are not interested in that part. Right now what we are interested in only what is the transmitted part of the beam. So also these white rays that are coming back, part of them will get reflected and get to the laser, but we are not interested in those parts of the rays which are going to go to the laser. Okay, they'll not disturb anything up there. Okay, so only part that is we are interested in is whatever is getting partially reflected. So you know this beam splitter thing, right? Okay, beam splitter is where the beams are passed. When beam is passed, part of the beam will get transmitted and part of the beam will get reflected. Okay, it's like a uh, only part transmission happens there. Okay, so and then like no part of the light is, so there you can get this beam split as 50-50 beam splitter or 30-70 beam splitter, or that kind of a specification you get for beam splitter. Okay, so 70% part gets transmitted and only like some part will get reflected, like that. There are specifications. Okay, so we don't get into those details, but like the idea is to kind of like split the beam so that one part of the beam gets transmitted, another part gets reflected in the perpendicular direction. So for these green incident waves rays here, like a part will get reflected in this direction. Okay, because the beam splitter has this mirror in this kind of a tilted fashion. Okay, but we are not interested in this reflected part that is going there. Okay, we are only interested in this point in the transmitted part. Okay, so also like these white rays, some part will get transmitted, which we are not interested. We are only interested in reflected part, and that's where that part goes onto the photodiode. Okay, so photodetector, when it comes, like these beams will look on the surface like this, and on the photodetector they'll look something like that. Okay, so this is like a reflected reflections of a beam on the photodetector. So these two side beams are going to fall on these two E and F areas, and the center spot is going to fall on ABCD areas. Okay, so if I say A plus B plus C plus D is going to be my data signal. Okay, so all that is falling on that center area, A plus B plus C plus D, will form the data signal. Okay, so if the data is not there, you'll get this full reflection here. If data is there, or either way, whatever. Okay, if the data is there, then I don't get this reflection. So A plus B plus C plus D will dim out when the data is not there, or when the data is there, whatever you want to say. Okay, for the lands, whenever it comes here on the instead of pits on the land here, then I'll see full reflection up here. Okay, and I'll see that, so that in that sense I can make out the binary distinction between the zeros and ones that are there on the surface of the CD. Okay, so that's how this data is read. Now comes to sensing. So now we want to sense whether the thing is on the track or not. For that, these are the two side beams that are used here. Okay, now these two side beams get reflected on E and F parts. Now imagine if you have some small error in the motion, and it goes off the track. Okay, so now the beam's position is something like this. Okay, so you'll find that the beam which is say on track E is now interfering with the data. Moment it starts interfering with the data, previously it was not, then its intensity is going to go down. Okay, so whatever you are getting on E is going to go down in the intensity, and that's how you say that okay, it has started moving in this direction. Okay, same thing will happen to this spot E. See, this spot E, spot F here has not yet started interfering with this other track. It's important to see that. Okay, they are a little closer to the central track than to other two tracks. So it's there. So the right position of these spots is not exactly in the middle of these two tracks. Okay, otherwise this will not happen. Okay, so there this position is a little more closer to the track that is getting sensed. Okay, so that's why when small motion happens this direction, it starts interfering with the track data and its intensity goes down. Moment its intensity goes down, we'll have to kind of see that okay, oh, this is alert error correction signal, and we'll move it in the other direction. Same thing will happen. So see, if E and F both would have started going down in intensity because F is now interfering with the other track, then our goal is lost. E and F we want E and F to be having a differential kind of a sensing, so that we have a tracking error nicely captured. Okay, so you can see that this F spot has not yet started interfering with this, but E has already started kind of quite good interfering with the data track. Okay, so the same thing will happen in the other direction also. Then F will start interfering with the data track, and this E has not yet started with interfering with this other data track, and then you will see the differential intensity signal will come. E minus F is going to kind of give you the tracking error. Okay, is that part clear? Any doubts or questions about that?
So,
Yeah.
so what if right now in this figure, in
Uh,
the three red, pink colored beams,
uh,
what if there was a land, I mean the black part right below the F beam.
Black part right
So
below
let's
the
say
F beam. Yeah. So
both
this is F
started
beam.
to dim
Uh,
out. Yeah, both started to dim
uh,
out. So still it
so
is wrong.
see what will happen is first E will start dimming out. E and F both start dimming out at the same time. Okay, that's not going to happen because there is a small kind of a see this land area here between the two tracks is much larger, but these spots are not in the middle of the land area to begin with. That's the important kind of a consideration here. To begin with, they are like no more closer to the data track, which is what we, this is a data that we are interested in. For this data track, it will be this spot will be closer. So these relative positions of these three spots is what is important. Okay, so they are adjusted in such a way that they are closer to the data track, but they are not touching to the data track in the normal kind of full position like this position. Okay, but I mean may not have drawn it really like that kind of nicely here, but this spot is more closer in the normal position to the reading data track than the neighboring tracks. This spot is also more closer to the reading data track than to the neighboring track. Okay, so then moment the small error starts happening either this direction or the opposite direction,
Got it.
like immediately it will start interfering and will get a differential signal. But at that time other F is, or say if E has started interfering, F will not interfere yet.
Got it.
But immediately once you see the error, you are going to correct it. So it will not happen ever like that. Of course, if you kind of like go past that correction and go beyond like that, okay, this is interfering, then like you are actually coming out of the closed, I mean the good control loop, which should not happen actually. So you'll have some kind of tolerances and design in such a way that this is not happening. Okay.
So
Yeah. Question.
please ignore the question if there's a lot of physics required. Why are there only 3 spots?
Oh, you're right. I mean, if you're right in your physics also, Pandey, that okay, there should be infinite number of spots. Okay, that's perfectly fine. Okay, but we are not interested in those spots because those reflections are not going to fall in any of these spaces here. One, and other thing is like the intensity, if you have seen this physics little bit more detail, like you will find that okay, when there's kind of a transmission grating happens for a laser beam, the central spot is much stronger than side spots, and then like as you kind of
Got
go
it.
away, like your side
Got
spots
it.
will diminish in the intensity also.
Yes, got it.
So
Thank you.
so their intensity also low, and they are not falling in the on the photodiode anyway. So we are not worried about them. Yeah.
Yes.
Good. It's good that I'm glad that you are thinking in physics and in all these different domains now. It's very good. See, that's what this like kind of a thinking is what is important in this course, or like in general for any development of a new conceiving a new system, like this kind of a critical thinking is essential actually with the practical thing and theoretical thing, both, I mean both domains. Nice. And we'll do like we'll do this is I think the very I mean I would say quite complex system. Okay, not all the mechatronic systems are this or like more complex than this, but like if you can understand and appreciate this particular system, a lot of different systems will be very like very easy to design for you. I mean it's not very difficult. You'll be able to design them very nicely. Say for example, you might have seen like the scanner system, for example, is very simple as compared to this, and you can relate whatever fundage we have learned from this system very nicely to the scanner system also actually. Okay, so if you understand this system well, like or the concepts that we are kind of taking away from this system well, then they'll help you a long way to design many different kind of interesting mechatronic systems. I'll give you some examples that we have done in our lab, but there is a lot of other things that can be possible. Okay, by just extension, further extension kind of thing of the concepts that we have learned or started this foundation. Okay, so this part clear, then we can move on to the focusing part. Okay, and focusing part
So
has that with physics. Yeah, Radha.
in the when the information, when the rays pass through the beam splitter, isn't information lost due
Yes,
to? So
yes,
how
you're
do
right.
you compensate for
We
what about
we
the?
use a stronger laser. That's it. So when the beam splitter, as the name suggests, it will split the beam, a part of the beam only what we are interested in. So we have to ignore the rest of the part which we are not interested in. That much kind of a intensity of the beam is lost. Okay, but it's okay. I mean, we use a laser which is little bit higher power, and we can do away with that. No problem.
Sir, can't something better be done? For example, like the tilted mirror. So
Uh,
it can be made to during the incident time, it can be made to be at that 45-degree angle or whatever, and
uh,
during the reflection, it can be made at some other angle, so that
no,
you
but
don't
this is
need a beam
happening.
splitter, then you get
But
another
how?
reflector.
Yeah, but then you need to move the mirror then, right?
Yeah, like periodically move the mirror.
But periodically, what is the period of that motion? Can you think about? See, when the data is coming and getting reflected, you are not stopping at any point to read the data on the surface. It's continuously moving CD. How fast you can do this motion, right? It's
Yeah,
very
correct.
tough to do
Yeah,
that
yeah, yeah.
actually. Yeah, and actually by saving this kind of a doing this kind of a additional thing, what we are saving from the practical perspective, we are saving just the laser power. I mean, the people have see 1 milliwatt to increasing the laser power from 1 milliwatt to 2 milliwatt is not a big deal. It's hardly any cost. If you think of your pointer lasers, that has some few milliwatts, 5 milliwatts of power. I mean, this is you need much lesser power for the laser which is there in the CD-ROM drive. So
Yeah, yeah, yeah,
that
correct.
perspective also we don't save much actually. See, I mean, people would do these kind of decisions based on their commercial viability. I mean, we don't need to be restricting to discussions for commercial kind of a perspective. I mean, we should do all academic kind of a possible explorations to just see, okay, what are the fund days there, like that. Okay, but yeah, that's the kind of thing.
Okay.
Okay, yeah. Now let's kind of look at this focusing part of it. So in focus, you see what happens is, oops, sorry. Um, okay. So let's see. So when things are out of focus, okay, in one direction, then the spot gets stretched in the elliptical kind of a fashion. Okay, in with like a minor axis of ellipse shifting, okay, its direction. Okay, and then major axis of ellipse or major axis of ellipse is is aligned to A and B or B and D and B spots here in this particular case. When the defocusing happens in other direction, so let me go to this slide here itself. Okay, yeah, and wanted to get this laser pointer here so that I can show you some stuff. Okay. So pen, let's get pen here. Okay, so you see that, okay, when we are at the focus, out of focus in this direction. Okay, so pen color yellow. Okay, so we are out of focus in this direction. Okay, this side. Then the ellipse happens. Okay, like this, for example. Okay, and when you are out of focus, so this is say position A here. Okay, so this is A when it is out of focus in this direction. Then when it goes out of focus in at the B side, on the opposite side, it will go like that. Okay, this is B position here. Okay, so this is B position B here. Okay, so when it is at completely at the focus, then only it is going to be a perfect circle. Okay, in one position it will have a major axis of ellipse in this direction. In other defocusing position it will have major axis of ellipse in this direction. This is how the rays travel. Okay, so in this kind of a spherical and cylindrical kind of a lens. So this, the lens has a combination of the spherical and cylindrical parts, as I said in the previous class as well. And that makes it behave in this kind of a fashion. The spot goes on one side elliptical in one major axis, and on the other side in the perpendicular major axis. Okay, like that the spot behaves. Okay, and in the center only at the focus. Okay, it is perfectly as a circle up here. Okay, and that's the reason, the focusing can be detected. Now so if this happens on now your photodiode ABCD parts as shown here. Okay, so oops, why focusing is not coming here? Wait. Yeah. So focusing on one side, it is covering like that, and in the other defocus direction, it will go A and C direction. So if I consider this signal A plus C minus B plus D, then it will have a error signal covered up there. Okay, and that's how I can detect whether it is in focus or it has gone out of focus. So is that part clear? Is there any question about this part again?
Sir, what is the parameter that decides which direction the focus is going?
We don't need to know that. We just need to know that, okay, if it is going in one direction, I have the signal positive, A plus C minus D, B plus D will be positive. If it is going in other direction, A plus C minus B plus D will be negative. That is it. I don't really need to know whether it is going positive up direction or down direction. I'll just I mean, of course, I need to move the lens in the appropriate direction. If it is not going in appropriate direction, typically people just change the sign and make it go in appropriate direction. So there are a lot of these small other kind of practical things where you know whether the sign is positive or not. It has a lot of physical way the system is, and how your sensors are, how their gains are, and all these kind of things affect actually. So we don't need to worry about. So if you say, okay, A plus, this signal is what is coming up, and I want to move for this signal positive, I need to move it in this direction, and then I can give a positive signal to the coils, and then the coils will move in appropriate direction. If that positive signal is taking the coils in the opposite direction, I'll just change the sign of the force that is given, and I'll change them to go in the proper direction. Okay, this we often need to do in the practical world, when we are kind of even configuring simple motor and the encoder system, you'll need to do that. Okay, what is the direction of encoder positive? That needs to match with the direction of positive force on the motor, or PWM positive, or whatever direction of the motor positive, that needs to get matched. Okay, they need to be mapped properly in the practical world, so that then otherwise the negative feedback will happen, and instead of stabilizing the system, it will destabilize the system. Okay, yeah. So is that part okay? Anything on this more? Yeah.
I want to ask, for example, if the displacement of the disk is too large for the compliant mechanism to cover up, will there be such situation?
Come again. The what is large for this to cover up?
There must be a range of this compliant mechanism, right?
Okay. So look, okay, yeah. So normally, like, you'll design the system to kind of like, satisfy the specification. So for example, this wiggling or like, the undulations on the CD surface are like, designed to be like, maybe within say 100 microns. Then like, this compliant mechanism or will be moving only like, plus minus 100 microns or plus minus 50 microns, that kind of a motion, and that will be sufficient. Okay, so you'll design the system to kind of like, do whatever things. Typically, it's not going to be like, more than 100 200 microns. I don't expect this motion of the like, undulations on the surface of the CD to happen that way. And beyond that, if it is there, I mean, if somebody has scratched your CD so much that the scratch is going beyond that, then it cannot focus. It will not work then. And they will say, okay, so CD has damaged. Okay, so that's going to happen. Yeah. Okay, so this is about the focusing system, and now like, you can imagine if these spots here on the track, the side spots are going out of focus, that can also be detected by the exactly same way. So instead of E and F, you will have other kind of like, four sensors like, A prime, B prime, C prime, D prime, and A double prime, B double prime, C double prime, and D double prime in the place of E and F. Okay, and then there also you'll correct for the focus of the thing. Then your compliant mechanism will be always maintaining the tilt also. Tilt will be also kind of taken care of. So if you need that kind of a precision, there are some kind of a CD-ROM drives I have seen. I'll see if I can get a picture of this photodiode. It's interesting picture to look at. Like, you can see that E and F blocks also are kind of showing like this split, ABCD kind of a split. Okay, so if this is clear, then like, maybe we can stop here and like, take up the scanner in the next lecture. Okay, and maybe I think it may be worthwhile to go over like, these more such systems. Maybe in the future at some point again we'll like, do some exercise with respect to some system like that, and that will form up our fundamentals of like, positioning and making these kind of a choices of different mechanisms and things like that more firm. Okay, now I would like you to pause and like, think over your own summary of lessons that you have learned. Okay, so I would like you to jot them down. Maybe these can be a very useful kind of a learning exercise. Say if you like, see something out, observe something, and then think about and see what are the kind of ideas which can be generalized for generally development of some similar kind of a systems. Okay, so that is what you need to kind of start getting that ability, so that whenever you open, just don't open from I just want to know what is there inside. No, we want to go beyond that and see not only what is there inside, but also what we can learn from it. Okay, what are the fundamentals, why people have done it the way they have done it inside. Okay, so that is what we want to kind of capture there. So you go ahead and like, think about, we have done so much of a discussion. Based on that, what are the kind of things that you can generalize from the thing. Okay, don't go beyond this point unless you have a listed kind of your own observations and conclusions of how do you generalize these things that you have seen so far. Okay, so once you are like, done with that listing, then you proceed. Okay, so I'm proceeding right now, but you can pause your video and then proceed next. Okay, so these are some of the summary lessons I can list. Okay, so you may have some more kind of things to add to it. So just think, okay, there might be some kind of a trivial or like, maybe trivial but important things that you might have learned from this, that may be important. Okay, so this is not an exhaustive list of everything that we have learned. For everybody, the learning would be different from like, making the observations about some things. Okay, so one of the important fundamentals here is to kind of see, when we want to kind of have a accuracy to be very, very like, fine accuracy positioning, say 50 micron in this case, then the rigid mechanical systems with the gears and other kind of a mechanism can be okay. 50 micron, 100 micron positioning, that can be very easily obtained by our rigid kind of mechanical systems with gears or other kind of stuff. Okay, of course you need to take care of backlash for sure. So again, backlash is difficult to handle in the controls. Okay, so that's why you see in CD-ROM drive you'll have a way to kind of take care of the backlash in the mechanical domain itself, so that you don't need to worry about that in control of backlash. Okay, one of the important things is that, okay, when we want positioning accuracy moderate, okay, not really fine, then you can go for these rigid mechanical systems that we had here, as a rack and pinion or screw type of a drive for cross positioning servo in the CD-ROM drive. Now when we demand very high accuracy, which is much lesser than 20 micron or nanometer kind of a range, then we need to employ different system. Okay, only rigid body systems may not work. In this particular case, we can employ the compliant mechanism system that will kind of do a job for a very good kind of accuracy with a good range. But there are many other kind of such systems that may be available. One of them is say piezo kind of a drives, piezo actuators. They can kind of give very fine kind of a positioning, but their range will be typically limited. So compliant motion systems, okay, or compliant motion platforms can be actuated by piezos also. Okay, nobody prevents you to do that. Okay, so for example, whatever is driven in the stage, that block that was compliant mechanism that was driven by the magnetic drive, that can be also possible by using piezo drive. But piezo drive, the disadvantage is that it will not give the range that is needed for the control to happen. Okay, so for example, piezos will typically have a range of maybe about 100 microns, but in here, if you see in focusing servo, you may need to go beyond maybe 100 to 100 microns overall kind of a motion. So typically, it is not used, and also piezos are costly. That's the other reason piezo might not have been used in CD-ROM drive. And for larger range, okay, of motion, you can combine this fine positioning and gross positioning together, as we have seen that is done in the CD-ROM drive. Okay, then this is another very important thing. Some of the examples we already saw. One needs to think in mechanical and electronics system. Electronic systems domain together. Okay, so this is like a mechatronics kind of a thinking that will happen here. Okay, and there may be always some smarter or innovative ways to design. So do not constrain yourself that, okay, whatever you are thinking is only the possibility kind of a thing. There might be some still, you can be open to maybe other possibilities. Then you'll start kind of thinking a little more and get to more finer thing. Or maybe when you experience some things are not really working so well, then also you'll have a opportunity to correct and go ahead. Then this components, now see, this other kind of a thing is that these components that you saw in the CD-ROM drive, the actuators or sensors or some plants, these kind of components can be useful for developing some other systems. Okay, or you can use the same fundamentals but may not be this component because of the power and size that is needed, but the same concepts can be employed in other domains. Okay, so I'll show you some of the examples of utility of compliant mechanisms, for example, in doing 3D printing. Okay, so that we have done in our labs. Okay, so that kind of application one can kind of think about from inspired from CD-ROM kind of a system. Okay, then you can have some examples of such a kind are the mechanical probing system for MEMS. Okay, this is another thing that we have developed, so that you have a compliant mechanism which is probing things mechanically. Typically there are electronic probes to check the ICs, okay, you have a pads, you make electrical contacts and probe some of the devices on the silicon chip to kind of see the response of the devices and things like that. But now you can have a mechanical probing, in the sense if you have a say micro cantilever, then you can have a tip of that micro cantilever actuated by a probe. Okay, probe is nothing but simple needle kind of a thing, which is now controlled by a force, in the sense if you give small touch to this cantilever, very tiny micro cantilever, like the probe which will be mounted on some kind of other compliant mechanism system, like a CD-ROM drive compliant mechanism system, and then what will happen is, even if you do a small displacement of the probe by giving displacement to the base of the cantilever in the CD-ROM drive system, base of the compliant mechanism in the CD-ROM drive system kind of a thing, then the cantilever will get controlled force. Okay, so the cantilever that you are kind of measuring is getting controlled force. Okay, so that kind of a way is called mechanical kind of a probing system. Okay, so this may or may not have been so clear right now, but think about this. Okay, if you want to kind of probe some mechanical device such that the force that I'm applying is very controlled force. Okay, but I don't want to use any kind of a mechatronics in the thing. I just have mechanical kind of a way of changing this force. Okay, how can I do that? Okay, so that is a kind of idea there. Then you'll have a lot of fine positioning system for biological cell handling, or biological cell stressing systems and things like that. There can be very delicate systems can be developed based on such a mechanism directly, or using the concepts from the mechanism. Okay, then now we'll switch and look at the next topic, which is on another mechatronic system, which is a scanner.